Hello viewers, welcome to Timas TV. Today we are looking at DC generator. DC generator, this is an machine, electrical machine that converts mechanical energy to electrical energy. That is from mechanical energy to from mechanical energy to electrical energy. Now it's using the principle that whenever a conductor cuts a magnetic flux, there is an induced EMF. There's an induced EMF which will cause current to flow if the conductor circuit is closed. So this is the principle that is guiding a DC generator. It has this component. We have this component. This has a fuel system. The fuel system. We also have armature windings. We also have armature core. We have commutator. We also have, finally, we have brushes. So these are the 5 major components that make up the DC generator. Here let's demonstrate how it works with the sketch diagram. We can have a stuff like this. I also have something like this, where this is your magnet we pull. We have the flux that is flowing that way, and we can label it. So we also have a conductor that cuts the flux in this direction 1, and also this direction 2, this direction 3, this direction 4, has this direction 5, this direction 6, and this direction 7, and this direction 8. Direction 8 until I'm getting back to 1. So this is how an EMF is induced in the conductor depending on the angle where the conductor cuts the flux. So we can demonstrate this with a graph. You can call this one EMF. This is the situation. We have this. So in this case, at this point, this is point 1. This is when the flux and the conductor is parallel, and the angle between them is 0. So hence we have a 0 EMF induced. So on getting to this point, we have point 2. This is a point where there is an inclined angle, and we have EMF that is induced. You can see it's not maximum. So at point 3, we have a maximum induced EMF. because the angle between the flux and the conductor is 90. So that is why we are having this highest, the peak induced EMF. On getting to this point, it reduced to 4, reduced comparatively to zero point 0.2. The angle it inclines reduces the induced EMF, and we also get to 0.5. 0.5 is also the same where the flux and the conductor angle is 0. So we have 6. We have the maximum induced 7. We have the angle until you get to 1. This is an EMF load that we actually notice in the DC generator, where the magnitude and the value of the EMF depends on the angle between the conductor and also between the conductor and also the flux. So on getting to this point, we actually realize that we can extend this diagram to have something like this. We can also repeat a sketch of this where we will have a stuff like this, and this is the conductor that we are talking about. So on getting to this point, we have something we call commutator that is divided for the operation of commutation. So in this case, we have a situation where the induced EMF will have to pass through what we call commutator. A commutator is a process where the induced EMF is actually converted to a DC signal. So with the help of commutator is what we call commutator. We call this one mechanical rectifier that actually does the conversion between the AC to DC signal. So it means that the signal induced in the DC generator is actually AC signal, but the output is further rectified and by the device called commutator, and that is when commutation takes place. So we further have another device that is very helpful. We call this device brush. Brushed. There are two, and they actually served as a link between the commutator and the load. So this is the load, and we have this. So this is a brief sketch of how the induced EMF is actually that is directed to the load. So now we want to actually look at EMF equation in a DC generator. So we have this that change in flux. Let's use this as flux is actually equals to number of pole multiplied by the flux. So we also have that change in time is actually 60 divided by n. That is the speed of the flux by revolution per second. So the induced EMF is always equal to change in flux divided by change in time. So this will give us this divided by 60 by this. So, and this will finally have this relationship where we have this. So the induced EMF per conductor, this per conductor is actually this divided by this. So, but the actual EMF will have to do with the the total conductor in the system. So we have that the total EMF induced is actually number of pole multiplied with the flux multiplied with revolution per second divide per minute divide by 60, and you multiply with the number of conductor and also A. A is the number of parallel parts. A in this equation is number of parallel parts in armature winding. So we have A to be equals to 2 in wave winding, wave type winding. We also have A to be equals to P in lap winding. So please take note of that. The armature windings type must be specified to actually know the number of parallel parts that is there. So the next on the list, we want to actually look at types of DC generator. We have types of DC generator is the next. We have two types depending on the position of the excitations, the field windings. So um, we have self-excited DC generator. We also have separate excited DC generator. We have two types. So let's take a look at separate field excited DC generator. We want to demonstrate this using a diagram, so we can actually have stuff like this, the field windings that will give us this, and this will be with the armature, which will have the load. So this is the voltage across the load terminal. Here we have armature winding resistance. We also have IA, armature current. We also have the induced EMF. So at this point, we have, this is the diagram for separately excited DC generator. So in actually knowing how to do this, so what we have to do is that there is a load for us to look for the armature current. The armature current in this system is the same as load current, and also V is the terminal voltage, terminal output voltage, and this has to do with the total induced EMF. You have to minus this with the dropped at the armature windings, which we're going to have this and this. So we also need to look at the power developed in the system. Power developed is actually the induced EMF multiplied with the armature current. And then finally, what about the power output, which is the power output is when you the power output is You want to multiply this with this, and this has a lot to do with um, this, this, and this. So this is the power delivered by the conductor. So the next one is self-excited DC generator. We have self-excited DC generator. In this self-excited, we have three types. We have series field excited DC generator. We also have shunt field excited DC generator. And we also have, finally, we have compound field excited DC generator. So in this compound field, we have two. We have short field excited DC generator, and finally we have long field excited DC generator. So at this point, we actually are going to look at their individual circuitry setup. So when we talk of series field, we are actually saying that the armature windings is in series with the field windings. So, and this is giving us, this is the output, this is the load, and this is V, and this is actually load. This is the armature. This is the armature current. We have the induce. We also have the resistance of the armature winding. So similarly to this, we realize that the armature current is the same thing as the load current, and also we have to also take note that the terminal voltage is actually let's call this is actually the induced EMF minus what the drops at the armature windings. It also has a minus the field windings. So this is actually the value of the voltage that will get to the load. And in this case, we have power generated is always this, and power delivered is always VL, which is the same thing as this minus this squared this plus this. So this is the circuit explanation of the series field excited DC generator. So the next we are looking at is the shunt field. We have the shunt field, and which is presented as we have the armature field like this. We also have the shunt field, this parallel to this. We have your load, and we also have this terminal. So in this case, we have your armature current, we have the induce, we have this. So in looking at, we have the shunt current. So we realize that the armature current is actually, this is load. Load current is actually shunt current plus load current. That is the total armature current. And we also have that the shunt current is the same thing as, this is shunt of the resistance, V divided by R shunt. So you have to take note of that. And V is the same thing as this um, minus the drop in armature windings. And also this develop is the same, and this delivered. This delivered is the same thing as um, V this, which is the same thing as this, this, and this. So that is the circuitry analysis with the equation of shunt field excited DC generator. So the next one we are actually looking at is a short, is a compound short field DC generator, which we have something like this, and we have the combinations of the field. This is your armature windings. We have this, and we also have this. This is this. So this is a setup for short field DC, short field excited DC generator. So we have this to be your shunt circuit. This is the resistance of that. We have this, and we have this, and we have S here. We have load, and we have V. So at this point, we have the armature current to be equal to this plus this. So we also have that the shunt current is actually going to be at this point we have G minus this divided by this. So this is the shunt current. We have also the V. V is actually the terminal voltage. Is actually this minus yes. So but the power produced is the same, and power delivered is this, which is this. So this is the analysis for short field and compound DC generator. So finally we have the long field. The long field setup is like this. Long field excited DC generator. We have this setup. This is the field. This is shunt windings. we have the load. So you can see this is shunt resistance, this is series field, this is your armature, this is this, and we have load, we have shunt current. So this is V. So your armature current, same thing as this plus this, and also we have your shunt current is the same thing as um, V divided by this. We also have V. V is equals to this minus EX. So the power developed is the same, and also power delivered is this and this, which is the same thing as multiplying this. So please, I want to believe that the explanation has given you the basic in understanding the operation, the construction, and the guiding principle of the DC generator. Thank you very much.